by talking a little bit about graph theory. We're going to look at some graph algorithms. And hopefully, this beginning part anyway should be mostly review. Okay, so a directed graph sometimes called a digraph, okay, is a graph G equals VE, where it's a pair G equals VE, where V is the set of vertices, and the singular, because I always get somebody talking about a vertice, is vertex, not vertice. And E is a subset of V cross V, is the set of edges. Okay, so each edge is an ordered pair of two vertices. In an undirected graph, okay, E consists of unordered pairs. Okay, and so there are a bunch of things where it's not going to matter whether we're talking about directed or undirected, and there are a lot of common definitions, but they're really two distinct but related combinatorial objects. So in either case, okay, the number of edges is bounded by the square of the number of vertices. And one of the conventions we're going to adopt is I'm not going to use, for the cardinality of a set, when it's in O notation, I'm going to drop the vertical bars. And that just saves with a lot of, because we do so much of our notation using O of E's and V's, and we'll just drop the vertical bars because there's no confusion here that we actually mean the cardinality of the set, not the square of the set. Okay, so that's just a simplification. Okay. Also, if G is connected, then the number of edges is at least V minus 1. Okay? And one of the ways we're going to use these two facts together is that in this case, when we look at the log of the number of edges, that's equal to theta log the number of vertices. Okay, because the number of edges is essentially going to go between slightly less than log n, log v, excuse me, to slightly, basically to a constant times log v. Okay, because log v squared is 2 log v. Okay, so if you're rusty on 6042 material related to graphs, let me encourage you to review the definitions in Appendix B of the textbook. Okay, so Appendix B has a whole bunch of stuff on this. So now we'll start into stuff which will be gradually, we'll get into, for people who've seen some of this, we're going to gradually get into stuff that's more and more stuff you haven't seen probably. So we're going to look at graph representations today for our algorithms. We're going to start out with one of the simplest representations, which is called an adjacency matrix. representation. Okay, and the adjacency matrix representation, what we do for of a graph, whoops, of A. Hey, this appeared again. Somebody fetched it out of the pit. Okay, is the let's actually simplify things for a second. Okay, where let's just for convenience the set of vertices are just the numbers from 1 up to n. Okay. Is the matrix A running from 1 up to n and 1 up to n given by A of ij is equal to 1 if the edge ij is in our edge set and 0 if ij is not in the edge set. Okay, so you simply have a bit that indicates whether the edge ij is there. So it's a matrix representation of the graph. And in weighted graphs, you'll find that instead of 1 and 0, you just represent it by the weight of the edge. Okay, so that's another thing that we'll see at some times, is that we use the weight of the edge rather than just a bit indicating the presence or absence. Okay, and so for example, here's a simple graph where we have 1 going to 2. Okay, so this is a directed graph. It's an undirected graph. This matrix is symmetric, right? Okay, is one way of representing it. Or you can represent it just with values above the diagonal. There are a variety of ways of doing that. Or else it's symmetric. But in the directed graph, that's the general, that's the more the place that this was developed for. I just make the matrix, and here's some. Okay, so let's see. So 1 is not connected to 1. Okay, 1 is connected to 2. 1 is connected to 3. And it's not connected to 4. Okay, so pretty straightforward. 2 is connected only to 3. 3 has no outgoing edges, so it's not connected to anything. And 4 is connected to 3 and not connected to the others. So that's an adjacency matrix of this graph. Okay, you see there's a, if I give you this, you can draw me that. If I give you that, you can produce this matrix. Okay. Now this representation is called a dense representation because the storage for this is order v squared. Okay, because I have to represent everything. And that's appropriate for some problems, but for some graphs, most of the elements here are 0. And if they're mostly 0, you don't want to represent them. Okay, for example, in a tree, okay, the number of edges is 1 less than the number of vertices. So in some sense, so therefore, you should be able to represent a tree with only order v entries. But here, it would use order v squared storage. Another example is a planar graph, a graph that can be drawn without any crossovers in the plane or on the surface of a sphere. Okay? So for a planar graph, it turns out that if the number of vertices is greater than or equal to 3, there's at most 3n minus 6 edges. Okay? So there are a variety of classes of graphs that arise in practice where you don't nearly need the quadratic storage required by the adjacency matrix representation. So instead, we look at sparse representations. And the most popular sparse representation is very simple. It's called an adjacency list representation. Okay. And essentially, the adjacency list of a vertex V and V is denoted by AdJ of V, okay, is just the set of vertices adjacent to V. Okay. So for example, for this graph, the one here, the adjacency list of vertex 1 is the set of vertices 2 and 3. And for vertex 2, what's the adjacency list for the vertex 2? Just the set containing 3, right? And for 3? Empty set, good. And for 4, so once again, 3, right? Okay. Now, for undirected graphs, the size of the adjacency list of V is just equal to the degree of V. Okay, it's the number of elements that is adjacent. For directed graphs, okay, the size of the adjacency list is what we call the out degree of V. Okay, so for directed graphs, we have a notion of an out degree and an in degree. Okay, for undirected graphs, we just have the notion of a degree, of the degree. Okay, so if I look at how much storage is required by the adjacency list representation, okay, so the storage is essentially order V, because I have to have at least V storage, plus the degree of each of the vertices, say for an adjacency list. So it's basically V plus the sum of I equals 1 to n of degree of I. Okay. And what is this equal to? What's the summation evaluate to? Harkening back to some very old, let's get those aged neurons firing here. What's the sum of the degrees of the vertices of a graph? Yeah. It's twice the number of edges, okay? So this is order v plus e, because this is just twice the number of edges, because of, and what's the theorem that tells us, the lemma that tells us that it's twice the number of edges? Who remembers these obscure combinatorial facts from 6042 or elsewhere? Okay, this is called the handshaking lemma. Okay, so there's a party, and various people shake hands during the party, and nobody shakes hands with himself or herself, and people shake hands maybe the same number, maybe different numbers of times. Okay, and at the end of the party, somebody goes around and counts up for each person, says, how many hands did you shake? And they add all of them up. And the answer is even. Okay, so that's the handshaking lemma. Why is it even? Yeah, because whenever you shake hands, it increases the degree of both sides by 1. So the sum of the total degrees is increasing by 2. So basically, it ends up being twice the number of edges is what you get when you sum all the degrees. Okay, so this term here, that's just equal to twice the number of edges by the handshaking lemma. Okay, so that's and so this amount of storage is nice, because if E turns out not to be its worst case v squared, but is, for example, as we mentioned, for a planar graph or a tree or various other graphs, is much less than v squared, then the storage here can be much cheaper to keep the adjacency list representation. Okay? On the other hand, there's a hidden advantage to the adjacency matrix representation. In the case when E is close to v squared, this is order v squared, but you have to sort of have, to represent a list or whatever, you have to have pointers and so forth. Okay? Whereas in this representation, I just need a bit for each edge. Okay? So this takes order v squared in the worst case words. This takes order v squared bits. And so this is far more efficient, okay, if you have a dense graph. But most graphs that we encounter in practice are not dense. They're sparse. Okay, so this is a sparse representation. Okay, because it takes storage that's linear. It lets you represent sparse edge sets efficiently. Okay, any questions about list representation, adjacency list representation? There are other representations for graphs, including other matrix representations besides an adjacency matrix. There's another type of matrix called an incidence matrix that you'll sometimes see. Incidence matrix, you basically have a matrix that maps vertices on one dimension versus edges on the other dimension. Okay, and every column is mostly zeros with a 1 if it's got, say, an out degree going to that edge, and -1 if it's got an in degree going to that edge. So that's another representation. Okay, and there are lots of different representations for, you can use an edge list representation. I just give you a list of all the edges, but they're not organized into what's adjacent to each number. So the edge 1, 2 might occur in that edge list representation very far from the edge 1, 3. So lots of different kinds of representations of these things. And one of the nice things about graphs and graph modeling is this is probably the single most powerful abstraction that we have in programming, is the abstraction of a graph. Okay? In fact, it's the single most powerful social phenomenon we've seen in our lifetimes. The World Wide Web is a graph. Okay? So graphs are omnipresent. Okay? And there's all kinds of things you can represent with graphs, as you will see on the take-home exam, quiz 2. Okay. This is all preface. Okay, so some of this I hope is review. Okay, some over here. Some of this may be new, but I hope that it's reasonably straightforward. Now we're going to get into some stuff that some of you may have seen, but many of you will not have seen. And the topic we're going to talk about today is a graph algorithm for a particular problem called minimum spanning trees. Okay. So for this problem, we have an input, which is a connected, undirected graph G equals VE, okay, with a weight function. In this case, it's an edge weight function. Function W that maps each edge to some real number. So that's our input. Now, for simplicity in today's lecture, I'm going to make an assumption that isn't made in the book. Okay? We're going to assume that all edge weights are distinct. In other words, they're all different from each other. There are no two edges that have exactly the same weight. And that will allow us not to worry about breaking ties in our code and in our theorems that we're going to prove today. Okay? In the book, we don't make this assumption. Okay? So in the textbook, you can go and read what happens, and you'll see that most of the definitions get a little bit more technically intricate, but not anything substantial. But it's just easier in the presentation not to worry about those cases, okay, so that we can cover more substantive material here. Okay, so we're going to assume that throughout the rest of the lecture. Okay, for output, for a minimum spanning tree algorithm, we want to produce a spanning tree T. Okay, and a spanning tree is a tree that connects all the vertices in V, okay, of minimum weight. Where the weight of the tree is just the sum of the weights of its constituent edges. Okay, so the weight of UV. Now you'll notice I've cheated here a little bit in my definition. I said we were mapping the weight function E to R, but here I've mapped ordered pairs. So what I really should be doing is saying W of open paren, U comma V, close paren. Okay, so you know me, I like to be sloppy. Okay, as long as we understand what we're doing. So I'm going to omit the extra level of parentheses, and I hope nobody will get confused about the type of this thing. This is a weight of an edge. Okay, so the weight of the whole tree is just the sum over all the edges in the tree of its constituent weights. So let's take an example here and see what this definition means. And this is going to be a running example. So Okay, so let's see. So I drew something that looked, I figured biology was in, so I drew something that looked vaguely biological. There's my hexane radical, or whatever those things are. Hexane radical, right? Yeah, okay. And then it's what? It's a benzene ring. Good, yes, that's right. I remember. So I had last had chemistry in high school. Okay, and that was before they discovered things like elements. You know. So the edges, I have 6, 12, 5, 14, 8, 3, 10, 7, 9, and 15. So how about, did I get them all? I think that's right. Okay, so today I brought the blue chalk so that we can now figure out what is a minimum spanning tree for this graph. So would somebody like to suggest an edge that they believe belongs to a minimum spanning tree? Yeah.
You both 9 and 15.
Yeah, 9 and 15. Good. So I only asked for one, but that's okay. There's 9. There's 15. Those belong because otherwise it's going to connect all the vertices. Okay? It better connect those, and these are the only edges that connect to those vertices. So these are definitely in the minimum spanning tree. Whoa, that's really fast. Okay, just one. So which one of those do you want to pick and tell me why? 5. Why do you think 5 is in? It is. Give you some confidence to.
It's the shortest distance from that vertex, so
Yeah, it's sort of like, how else might you connect this guy up, right? Sort of. Yeah, we'll formalize this a little bit later. Okay, and then you said 6. Okay, because it's got a choice of 6 or 12 to connect it to the rest. So you might as well pick 6, because 12 seems. Okay. What else here? Yeah. 7. So why do you think 7's in? Yeah. Otherwise, because you ended up connecting it through here, so no matter how we get these connected, it's always going to be cheaper to do this one. Right? So we had a choice of those two edges. Yeah. The 8. Good. Okay. Just because why? It connects which one? This one? Yeah, I mean, 3 connects it a little bit cheaper, but then I wouldn't be able to connect this up as cheaply as I could do that. And this one is more expensive than that. Okay. Any others? Yeah. 3. Now, this is actually quite an interesting thing you folks have done here, because normally, when I do this, people pick 3 first. It's the lightest edge in the whole graph, right? I mean, okay, so it's the lightest least weight edge. So the 3 is definitely there. So I think that that's a minimum spanning tree. Is there any? So one of the reasons that I wanted to have no edge, all edge weights are distinct, is so that the minimum spanning tree would be distinct. Otherwise, you have to talk about a minimum spanning tree. As for example, if all the edges had weight 1, then any spanning tree would be a minimum spanning tree. So once again, it's this language issue of the versus a. And by making all edges distinct, it turns out that the minimum spanning tree is unique. Okay? So is this indeed the best one? Is there any way of improving this? Is that what I got? Is there a way of improving this? Or is this the best? Well, is there any way that, say, 12 could be in the minimum spanning tree? Somebody give me an argument that 12 can't be in the minimum spanning tree? Yeah.
You already have like a path to it that's 11, so like 6 and 5 is a path that's 11.
Okay.
Less than 12. And those are the two. I don't know. Never mind.
That's okay. I think you've got the right idea. But I don't think you have to worry about the sum of these. You just have to compare them. If I put in 12, I have to delete either 5 or 6, right? Because this makes a cycle, and trees don't have cycles. Okay? So if I put in 12, I have to delete either 5 or 6. Those are both lighter. Okay? Less weight. So I wouldn't ever want to do that, because that would only increase the weight. Okay? And I think a similar argument can be made for 14 if I look at this cycle. Okay, if I put this in, one of these edges has to go. Okay? If I put this one in, then one of these edges would have to go. Okay, so we're going to see arguments like this. Now that doesn't show, that just shows that this is sort of locally optimal. It doesn't show that it's globally optimal. We'll get into that in a little bit as we explore minimum spanning trees. So the first thing I want to observe, and perhaps you'll observe it with me, is that there's actually an optimal substructure property working here. Okay? So there's actually, oops. So I take a look at some minimum spanning tree T. So let me just do a schematic of a minimum spanning tree. Okay, so this is the minimum spanning tree. I haven't shown the other edges in G. So this is only showing edges in T, not the edges in G. The edges in G have been evaporated. Okay? So we're only looking at the edges of T, but the edges of G are still there. I just didn't draw them. Okay? So let's take a look at this. Suppose that I pick two vertices, adjacent vertices, there's an edge, UV. So I take U here and V here, and I look at this edge, and I remove it. Move any edge, UV, in T. So let's go ahead and remove it. Okay. What does that do when I remove it? Well, it produces two subtrees. Because whenever you remove an edge from a tree, you get two subtrees. So we'll call these T1 and T2. Okay, so those are these subtrees. Okay, so T is partitioned into T1 and T2. Okay, and let's just look at T1 for the moment. Okay, so we're going to have a theorem that says the following. The subtree T1 is the minimum spanning tree of the graph G1 equals V1 E1. Okay. How did I phrase this? The subgraph of G induced by the vertices in T1. Okay? So what do I mean by the subgraph induced of G induced by the vertices in T1? What does that mean? Yeah. Right, exactly. You just take all of the edges of G where both endpoints are vertices in T1. So we can write that formally. So V1 is just equal to the vertices of T1. Okay, all the vertices in that tree. It's a spanning tree. If I remove an edge, I still have all the vertices. Some of them belong to T1. Some of the vertices belong to T2. And we're talking about V1 being the set of vertices in T1. And E1 is just the set of edges in the graph in E such that sorry, I shouldn't use U and V. I should use X and Y because I used U and V up there. X and Y. Such that X and Y are both in V1. And that's the subgraph induced by the vertices in T1. Okay? So people follow what this is, what this definition says? Okay, and similarly, I could say the same theorem for T2. Okay, so it says that we have an optimal substructure because if I look at the minimum spanning tree for T, in there are minimum spanning trees for subgraphs. Okay? That's an optimal substructure property. Okay, and what's optimal substructure a hallmark of? Dynamic programming. Okay, so I don't have to find this kind of graph by, for example, checking every set of n edges to see if it's minimal. You know, I'm going to be able to use more powerful techniques. So let's prove this theorem. Okay. As with a lot of optimal substructure theorems and other theorems of optimality that we'll see, there's 3 words that describe the method that we use to prove this. So who remembers from last time those magic 3 words? The middle word is and. Cut and paste. Very good. Okay? Cut and paste. Okay, that's how we're going to prove this. So what do we have? We have that the weight of T is just equal to the weight of UV plus the weight of T1 plus the weight of T2. Okay, because each of these is just the sum of their component edges. We've said that if we remove UV, we get T1 and T2. So if we add up all the weights of all the edges in T1 and T2, okay, then and add that to U and V, we've got the weight of all the edges in T. Okay? Okay. So let's suppose that T prime, T1 prime, okay, is a better, meaning lower weight, spanning tree than T1, okay, for G1. So suppose T1 prime is a better spanning tree than T1. What could we do? Okay, so I find some better way to connect up those vertices in that loop up there. Okay, I have a better way to connect them up. Yeah. Yeah, I can make a spanning tree that's better. Okay, and what exactly would that spanning tree be? That would be T prime is equal to what? What's the spanning tree? Well, of UV. Okay, would be better than T for G. Because basically if I'm lowering the weight of this, okay, any other way I have of connecting up the vertices of T1, okay, using T1 prime, if I just add the edge over to T2 and connect it up to T2, I'm going to end up with a lower weight spanning tree, contradicting the minimality of T. Yeah? T1 prime. 1 prime. Good. Sorry? Yeah? Well, this is true for any UV, right? I mean, so I can remove any edge, and I've got an optimal substructure property. Okay? So yeah, this is true for removing any edge. In fact, let's emphasize that. Any edge UV. Okay? So this is a very typical cut and paste argument to argue that something is minimal. Okay? And so we can apply this theorem in over here, for example, and say, well, you know, let's remove this edge, for example. Okay, is this the best way of connecting up then these 4 vertices, which are all connected? Well, there's only one way of connecting up these 4 vertices. That's connecting those. And so therefore, we know that the ones we picked here were really the best. Okay, and over here, what's the best way of connecting up these vertices? Okay, so we can figure out what's the best way there. Okay, and so the point is this is the best way for those. So we actually can factor out our problem. Okay, so this is the optimal substructure. What's the other hallmark of dynamic programming? Overlapping subproblems. Do we have overlapping subproblems here? We're going to have a property that some subproblems are going to be similar to other subproblems? Well, sure. You know, depending upon which of these edges I remove, I've got problems and I've got subproblems. Okay, so yes, we have overlapping subproblems. So that's great, because it means then that dynamic programming may be a good way of solving this problem. And that's all true, but it turns out I've been leading you down a garden path. Okay? There's actually an even more powerful property operating here that makes an algorithm, we can come up with an algorithm that's even more efficient than a dynamic programming algorithm would be. Okay? And that is a property which is a hallmark for what we call greedy algorithms. And one of the things that you'll find is often you come up with something, you say, oh, dynamic programming will work. But in fact, it may be that you're lucky enough for your problem that a greedy algorithm will work. So this is a hallmark for so-called greedy algorithms. Okay? And greedy here is a technical term. Okay? But it means very much what we mean. And the hallmark is that there is a greedy choice property. Okay? Which says that a locally optimal choice is in fact globally optimal. Okay? So for example, what is the greediest thing? If I wanted to connect things up, what's the greediest I could be in this particular problem in picking an edge? If I want to minimize the weight. Yeah. Pick all the shortest ones. Well, the shortest ones might form a loop. The lightest ones. But they might have a loop, the 7 lightest ones. I want to be even greedier. I don't want to try to get as much, however. So take the lightest one. Okay, and in fact, it's a theorem that the lightest edge in a graph belongs to a minimum spanning tree. Okay, and if it's unique, then it's minimum spanning. So here, 3. That's as greedy as I can be. I want to connect things up. Okay, and I don't want to waste any edges. Let me just go after the lightest thing. It turns out that guy's always in there. Okay, but in fact, there's an even more powerful greedy property operating. So we'll state that as a theorem. Okay, so it's true that 3, the lightest edge there. In fact, you could also say the lightest edge coming out of a given vertex. That's another way to be greedy. Take the lightest edge coming out of a vertex, and that's going to be in the minimum spanning tree. Okay, but there's actually an even more general statement than that. So let's let T be minimum spanning tree of G equals VE. Okay. And let's let A be an arbitrary subset of V. So some subset of edges. Okay. And now suppose that some edge UV is the lightest edge, the least weight edge, let me call it. Connecting a vertex in A to a vertex in V minus A. Okay? Then this edge, this lightest edge connecting these two sets is in the minimum spanning tree. Okay? So for example, in this example, let's suppose that A is the bottom 4 vertices. And V minus A is then the top 4 vertices. And what's the lightest edge, okay, the least weight edge that connects the top 4 vertices to the bottom 4 vertices? The 7. Is it in the minimum spanning tree? Sure is. Okay. Let's take just the top vertex there as A, and all the other vertices as V minus A. What's the lightest wedge edge connecting that top vertex to all the other vertices? The 6. Okay, and it's in the minimum spanning tree. Okay, so this is a theorem. Okay, I don't have to check every one of them. Okay, you can just hopefully believe me a little bit. Okay, so let's prove this. Hey, everybody understand what the theorem says? Anyway, I want to partition the edges. It's going to give me so when you partition edges into a set and its complement in the graph, that is those edges that aren't in that set, that's called a cut of the graph. It's a way of dividing the graph into 2 parts. So let's suppose that this lightest weight edge here, UV, is not in T. Okay? So what technique do you think we're going to use to show this property? I'll give you a hint. It's got 3 words, and the middle word is and. Okay, so cut and paste. I should have said there are 3 words. I should have given the complement, right? The 3 words, the first word is cut and the last word is paste. Okay, so we're going to cut and paste. So let's take a look. Here's my minimum spanning tree. Okay, and I always want to make this look like some dragon or something. You know, be creative, be more artistic. Okay, so let's see. So this is going to be, so first of all, we have to pick a subset to be in A. So these guys are going to be in A. Here's one, and here's one. It's in A. And these 4 are all in A. Okay, and I'm going to pick this one to be in A. Okay, and this one to be an A, and these two to be an A. Okay, so those are all an A. So if I have that and that, these are in A, and these are in V minus A. Okay, so this is my graph, and now what I do is, so I've got a minimum spanning tree, and I have a subset in V, and now I have my edge UV. Okay, so that's the least weight edge connecting a blue vertex to a black vertex. Always, when you're on a blackboard, you're always tempted to say white vertex and point to the black vertex. Okay, so blue vertex to a black vertex here. Okay, so let's say that this is U here, and this is V. So I have some edge there. And I claim this is the lightest edge. Okay, it's the least weight edge. Connecting something in A to something in V minus A. And notice it goes. It goes from A to V minus A. Okay? So how now can I find, what can I do here to sort of do a cut and paste argument to make, to show that this least weight edge should have been in the minimum spanning tree? So is there another edge that doesn't belong in the minimum spanning tree? Somebody point to an edge in this graph that doesn't belong in the minimum spanning tree? This is the least weight edge of any that connect something in A to something not in A. Yeah? This guy. Why do you say that shouldn't be in the minimum spanning tree? So this, adding this edge makes a loop, okay? And in particular, there's a unique path in the unique simple path meaning that it doesn't contain any repeated vertices or edges, okay? It's a unique simple path going from U to V, okay? So somewhere along that path, since U is in A and V is not in A, somewhere along that path, I must encounter an edge that goes from A to not A. In this case, I encounter this edge. Okay? Now, why is this edge not in the minimum spanning tree, even though I said it was? Where's my contradiction coming in? Why is that one? Yeah. Yeah, UV is lighter than that edge. So if I delete that edge and add in UV, I've got a lighter spanning tree than the minimum spanning tree. Can't happen. Contradiction. Okay? So let me just reprise that argument. Okay? So if we consider the path, the unique simple path, from U to V. And in particular, there are in Appendix B of the textbook, there are 6 equivalent properties of trees. Okay, and I encourage everybody to reread that section. It's reprising some stuff that you may have had in 6042, but I encourage you to go through and look at those 6 properties and make sure that you understand what those 6 properties are saying and why they're all equivalent. So So we look at the unique simple path from U to V, okay, in T. Okay, and now we swap UV with the first vertex on the path, sorry, first edge on the path, that connects a vertex in A to a vertex in V minus A. Now, one of the important things when one is doing this kind of proof is to argue that these things actually exist. So if I've got an edge UV, okay, that's not in it, then we know that adding an edge forms a cycle. So we know there's a path from U to V. Okay? And we also know that there must be some first edge that connects A to V minus A, because U is in A and V is not. And so it can't be the case that as we go along this path, we always have edges that are not in, both of whose endpoints are in A. Because when we end up, we have a vertex that's not in A. So therefore, somewhere along the way, there must be that first vertex. Okay? And then we swap with that, and that produces a better tree. Okay? So better tree results. Okay, any questions about that proof? Okay, another good example of a cut and paste argument. Really good example of a cut and paste argument. Okay, let's do some code. Okay, Prim's algorithm. Now, it's always a pain when you have algorithms that are named after people, because you never remember what the algorithm does, right? You say, and then people's names, right? Could be worse. Could be Lyserson's algorithm, then you'd never remember the name. Okay, so Prim, by the way, was a researcher at Bell Laboratories. And based on this algorithm, the phone company started to come up with a charging scheme for phones that charge not based on where the call actually was routed, but using a minimum spanning tree distance. So they could, if they took a minimum spanning tree, they could charge up to the cost of a minimum spanning tree distance between the 2 points. And as a result of that, he ended up as vice president of AT&T, very wealthy man, okay, very smart man, and it all started with algorithms. Okay, so what's Prim's idea? Okay, so he says, let's maintain V minus A as a priority queue. Okay, and we're going to key each vertex let's call that karate Q Q. Each vertex in Q with the weight of the least weight edge, connecting it to a vertex in A. Okay. So we'll see how this works in a moment. Let me write up the pseudocode, and then we can, let's see, so how do I want to write up the pseudocode? Let's write it on a nice, fresh new board. Okay. See if I can get this right. So I'm going to leave some space on the left side so we can do some analysis on the left. Q gets V. So that's the code. I'm sorry that the chalk is showing through. It makes it a little bit hard to see that. Okay. So let's see what's going on here. So we have a key. We're starting out the key of all the nodes as being infinity, because they're all initially in the set V minus A. A is the empty set. So the distance to things in V is the empty set. And we start an arbitrary guy as our start vertex. Okay, and what we're going to do is grow a tree. Okay, so this is always a good lecture to give on Arbor Day. We're going to grow a tree, okay, to make it span the whole graph. Okay, and the way we're going to do that is we're going to look at all the things in Q, and as long as it's not 0, we're going to take an element, the minimum element, out of the Q, and we're going to look at all the edges in its adjacency list, all the vertices in its adjacency list, and examine essentially all the outgoing edges. And if the edge goes to, when we take it out of Q, we're now putting it in the set A. That's what we mean by taking it out of Q, because Q maintains V minus A. Okay? So Q maintains V minus A. Okay? And so now what we want to do is say, okay, now let me figure out for every vertex that's now still in the Q, let me compare what the weight is that I have, and if it's less than the weight that it used to have there, okay, if it's less than that weight, let's update the weight. Okay, change the weight. And so actually what's going on here, and this is implicit, is there's actually a decrease key operation required here on the priority queue, because when I change a value in the priority queue, I'm going to be lowering it, okay, and it's a min priority queue, okay, and so therefore I have to update the priority queue, and that code isn't shown. Okay, and then what I do is I set for V, I say, well, U is responsible in some sense for that minimum weight edge coming out. And so I set its responsibility in this vector pi. Okay? And so at the end, T is essentially the set of edges V pi of V. Okay, all those edges form the minimum spanning tree. With the exception, which I didn't put here, of S, which has no, for which nil will be the pi of v. So there are actually only v minus 1 edges here. Okay, so this could be v, okay, for v not equal to S. Okay, so let's see how that works. Okay, so we'll do it on the example up here. And George, could you just follow along here as, because there are a lot of key punches here, just to make sure that we, and then when it's over. So we start out by giving everybody infinity as their distance, except for one guy. I'm going to start here, 0. Okay, and what I'll do is I'll mark them this time so you can see as we get the values. Okay, the distinction between the tree that we know is there versus the one that we're going to compute. So the first thing I do is I extract this element, so I take it out of the set. So how shall I mark that I take it out of the set? Let me double circle these. So this is now out of the set. And so what I am supposed to have in the set as a key is the least weight edge connecting it to things that are in A. So this double circle means it's in A. Single circle means it's in V minus A. So this is now in A. So in order for these to be correct, I've got to update. So I take a look at this edge and I say, 7 is less than infinity. So let me make that be 7. And I change its pointer to point this way. Okay, it's pi vector. And I do the same with the next edge. Okay, so this becomes 15. And points in. And this becomes 10. And points in. So now I want to find the least weight edge, okay, connecting connecting A to V minus A. And how do I find the least weight edge? Well, every vertex has with it its lightest edge connecting it to the things in A. So I just have to take whatever the minimum is here, and what's the minimum here? 7 here. Okay, so that's the least weight edge. And so I'm using the theorem at this point. Okay, by taking the minimum element, I say, I'm going to take that. Now, we already know that it's connected by this particular edge. So what I do is I remove it. Okay, and now I go through the update process again. I check all of its incident edges, and it's got 4 incident edges. Well, this one I don't bother to update because I don't have to, because it's not in Q. It's got to be in Q. Okay, but this one I can update, so that becomes 5. And this one becomes 7. Oh, and I also changed the pointer. This one becomes 7. Whoops, 12. This becomes 12. Change the pointer there. And 9. Change the pointer there. Okay? Now what's the minimum weight edge? I mean minimum weight vertex that determines the minimum weight edge connecting the two. It's 5. Okay? So we take that out. And we go and we look at all the incident edges. So we get 6. That's less than 12. So we make this be 6. And now that's no longer where this vertex is going to point because we've just updated it. So that goes back to normal, and we make it point in this direction. Okay? Then we look at 5. Well, that's already in the set. We look at 8 here. 8 is less than 10. So we update this one. This becomes 8. We make the pointer point back here, which means it doesn't point this way. Okay, and then we go here, 5. It points back that way. Sorry, 14. Sorry. Good. Somebody's on the ball. Okay. Now which one do I go for? 8. 6. I was just testing. Okay. 6. Okay, and we look, and its incident edges are both already in the set A. So then I go to 8. Okay, and now I look, and that's in the set already, that's in the set already, but this one isn't, 8. So this one goes to 3, and I point in this direction. Okay. Now where do I go? 3 is the least weight edge. Okay, and all of its incident vertices are already in the set A. Okay, then I go to 9, and all of its incident vertices are there, and then 15 and all of its incident vertices, adjacent vertices are in. Okay, and now did I end up with what I said I wanted? No, because when I moved this one, I forgot to move this one. Forgot to eliminate that. Can only have one. When I updated this, I neglected to update that. Now, is that right? So you see, each one points in the direction of who's sort of responsible for bringing it into the set. Okay? Magic. It's great stuff. Great stuff. Okay. Need my notes back. Okay, let's quickly do an analysis of this. Okay? So I'm sorry this is going to run over about 5 minutes. Sorry about that. So this part is order V. Okay, to update these. I have to write a loop for this. I didn't write the loop. I did it implicitly, but there's a loop there. That's not going to be important. Okay? How many times is this whole loop executed? How many times do we execute this statement there? How many? 6? Well, in general. V times. Good. V times. Okay. So in particular, it means that they're going to be V extract mins. Okay. And then in here, I have another for loop. How many times do I execute this for loop? The degree of U, right? Okay. So this is going to be executed the degree of U times. And the most important operation in here is going to be this decrease key operation. All the other is constant. Okay? So how many times overall do I do a decrease key? Through the whole, I'm going V times each time the degree of U. How many times am I executing decrease key? Yeah, basically order E by the handshaking lemma. Let's hear it for the handshaking lemma. Okay, so they're going to be order E of these guys. Okay, because the handshaking lemma is I'm just summing up the degrees of every vertex. That's how many times I execute the decrease key. So we can come up with a formula for the time. If I throw away some of the low order terms, it's going to be order V times the time to do an extract min plus order E times the time to do a decreased key. So let's, now the question is, how do I implement my priority queue? So what's the obvious answer? Yeah, heap. Okay, but let's start it with an even more obvious attempt. Okay, so we have Q T sub extract min, and then T sub decrease key, and then the total time. So if this is just a simple array, an unsorted array, I can find the minimum element in order v time. And a decreased key I can do in constant time because I don't have to do anything. So the total then is what? Order v squared. Okay? Now if I use a binary heap, okay, extract min is order log v, and decrease key is order log v. So the total time is what? E log v. Is that better than this? Sometimes. Sometimes this is better. Like, for example, if the number of edges is v squared, it's a dense graph, then this is going to be a better way to implement the algorithm. Okay, now there's a data structure that's described in the book that we'll talk about some more, but we're not going to actually study how it works, called Fibonacci heaps. Okay, and they have the nice property that extract min is order log v time, but amortized time. And decrease key is order 1 amortized. So what's the running time for this? Just add it up there. We could order E plus V log V. Okay? Amortized? Worst case. Okay, remember that the nice thing about amortized analysis is we can assign some amortized costs. When we add them up, we get the worst case costs. And what's nice about this is at least as good as this, and it's at least as good as this. Okay, and so that's the best algorithm, deterministic algorithm. The very best algorithm for this problem is an algorithm due to Karger, Klein, and Tarjan, which is a randomized algorithm, and it was discovered in 1993. This problem, by the way, is very old. It was discovered in Prim's algorithm dates from either the 50s or early 60s. I mean, really early, okay? And it wasn't until 1993 that an order V plus E algorithm was discovered. And one of the, that was the topic of David Karger, who's one of the faculty member in our theory group, his PhD thesis. Discovered that. Okay, sorry for running over.